recording.
Okay, so hi everybody. It's a pleasure to present Professor Nicolas Burq. Professor Burq is a professor at the Universities of Paris-Saclay. He's member senior of the Institut Universitaire de France, and he has a lot of distinctions, like he was one of the invited speakers at the International Congress of Mathematics in Heidelberg in 2010. He's a member senior of the Institut Universitaire de France. I already said that because I am reading. So he's really a very, very good mathematician. He's a specialist in PDE, control theory, asymptotics, and all that. He has more than 100 papers and a lot of citations. So it's really a pleasure to have him here. So you can start, Nicolas, please.
Okay, so thank you very much for both the invitation and the presentation, Luz. It's for me a great pleasure to be with you. Okay, so what I'm going to speak about today is based on a joint work with Hui Xu, who is actually a postdoc in New York University in Abu Dhabi. Okay, so this is about control. So the talk will be in two parts. So first part will be slides, and then in the second part I will try to give you some elements of proof, and I will switch to a handwritten tablet to go not too fast. Okay, so the problem is actually a very simple one. So we do there should be an I here. So it's and there should be an I here too. So I look at the solution to the linear Schrodinger equation. So it's I dt minus Laplace u is equal to 0, with u on the boundary 0 and the initial data u0 in L2. For the heat equation or Schrodinger equation, you have an observability which would be something like that. So you can measure the state at time t in terms of an observation, and you can have something similar for the Schrodinger equation. And for heat equation, there have been a lot of results about observation from domains which are measurable in time, and we can even go below something like that. So there's a big list of people, and I apologize if it's not that if I forgot some people. Of course, I did forget some people simply because the list is too long to put on a single slide. So I just put the one I know best. So for me, the two seminal results were results by Lobo Robiano and Fursikov-Imanuvilov, essentially at the same time. I don't know exactly at what time the papers were published, but essentially very close in time. And they were requiring coefficients to be reasonably smooth. And they were writing some observation estimate and hence control estimates using some open space-time sets. And then there was, I would say for me, it's a breakthrough by Miller, who really put up this in a very nice functional setup. So there is no new result with Miller contributions, but the result of Miller, the contribution of Miller is really that he was able to put all this in a very, very nice abstract framework, which allowed then many of the subsequent works. So then there's a big breakthrough by Fung and Wang in 2013, where these two authors were able to prove observation with measurable in time sets, and then open in space because they were using Kahneman estimates. And then some results by Aprise, Escoriaza, Wang Zhang, where they do measurable space-time. And then we had some contributions with Ivan Moyano, much more recent, were really able to really relax a lot of the assumptions. And then we can very much go very far in the understanding for the heat equation. For Schrödinger equation, the picture is much less well understood. So there are some very partial results saying that if you want to prove an observation estimate, then the most robust result is due to Lebot in 1989. And it states that the geometric control condition is such the assumption that all geodesics are going to enter the control region in time, in finite time. So I will later in the proof draw a picture, and if I forget to draw a picture, you can just remind me to do so. And then Lebot's result, following some breakthrough result on the wave equation. So Lebot's result in 1989 was that if you assume that the geometric control condition holds for an open set, meaning that if all the geodesics, all the rays of geometric optics enter this domain after time t0, and these rays are reflecting on the boundary according to the laws of geometric optics, then for any positive time, you have observation on time t, time omega. You see, so your observation set can just be 0, the interval in time 0t, time omega. And then, of course, by duality, you also have control for your equation. Now, what the result, the kind of result that I want to speak about today is the following. So, if you are working in the framework of Lebot, then you can drop the assumption that you are working on a time interval. So to have observation or control, you just need to have a measurable set in time of positive measure, of course, otherwise you're not going to see anything. But any positive measure set is going to work. Okay, so this is the kind of result that I want to understand. Can we relax the classical results for observation for Schrödinger equation to get some results for some positive, well, the ideal situation will be space-time sets, but we are not there yet. Now, presently, we can do at least positive in time sets. Okay? Now, on the torus, it's possible to go beyond this. And on the torus, there's a long history about observation and control of Schrödinger equations. And the results started in the 70s, and they were not about Schrödinger equations. They were about eigenfunctions. Of course, eigenfunctions are some special case of solution to Schrödinger equations with a very simple time dependence. You have an oscillatory function in time, e to the it lambda square, where lambda square is the eigenvalue. And so it's particularly simple. And people in the 70s, so with Zygmunt and Kohn, so Kohn is Bernard Kohn. He's a guy who just did this in mathematics and then quit and went to industry. And so what they proved is that for eigenfunctions, you have observation, and the Zygmunt's result was the fact that in dimension 2, you just need to take a measurable set, and Kohn's result was that in higher dimensions, it's enough to take an open set. And the motivations were not control theory. None of them did any control theory result, but it was really some harmonic analysis results. And basically, it was the Cantor-Lebesgue results. It was something like people at the time were very much interested in this kind of questions. And it was if you consider a sequence Fn of eigenfunctions that converge pointwisely to 0 on a positive measure set, and then what you get from this Zygmunt set is that then it has to converge to 0 strongly in L2. And it's actually a consequence of observation. Okay, of course, on the torus, you have the eigenvalues are integers. And so by using Parseval inequality, the observation of eigenfunctions is equivalent to the observation of Schrodinger equations with a time set which is 0 to pi. Well, you can go up to any time set which is length larger than pi. But I say it again, this was not the motivation of neither Zygmunt nor Kohn at the time. And I think none of them ever made the connection between their results and control theory results. To the best of my knowledge, the only person who saw this was much later, and Marius Tuxnack understood this. So I think it's in his book that this, in some sense, control for Schrodinger equations on tori date back to the 70s. Okay, so now what is known for the observation of Schrodinger equation on the torus? Well, on the torus, then the story for Schrodinger started actually much later with results by Arrow and Jafar. So you see it's almost, so you switch from the 70s to the 90s or the end of the 80s. So it's more than 15 years later. And neither Arrow nor Jafar were aware of this Zygmunt and Kohn result. So it's really some kind of a parallel story. And so what they did is that they proved on the torus that you had observation for potential equal to 0. And then you had to take space-time sets which were open, meaning, of course, if you take open in time, it means that you have an interval. And open in X is just you have an open set. Okay, so of course, an open set on the torus does not always satisfy the geometric control condition, meaning that this is stronger. In this particular case of the torus, this result by Arrow and Jafar is stronger than Lobau's result, which actually was not proven at the time. So Lobau's result is 80. When was it? It's almost 89. So it's essentially very close, essentially at the same time. Okay, and now there was an extension of this result by Komornik, Macha in higher dimensions. Also, it was always open set. So you can just think open sets as the product of an interval in time times an open set in X. And then we started working on this topic with Zworsky in 2012, and we were able to show that the result was still true for smooth potentials. So what is easy is small potentials, because you can just, if you take a small potential in L infinity, then it's just a perturbation argument shows you that it's going to be true also. And now if you want to get large potential, it's a different matter. Becomes more complicated. And then results by Anantam and Macha, Riemann integrable. And then we proved in dimension 2 with Bourgain and Zworsky that square integrable potentials, just think L infinity potentials were okay. And then Bourgain in dimension 3 was able to prove that bounded potentials were also okay. And then all these results were obtained for open sets. And now we continued working on this topic, and we finally were able to prove that in dimension 1 and 2, we could take a scalar product, a product of an interval in time times a measurable set in space. Okay, so you really try to reach. And of course, the big conjecture we have in mind on this question is the fact that the result should hold for any bounded potential and any measurable observation domain space-time. Okay, this is what we want to prove. Okay, Okay, so actually our result is not that good. So it's what we believe to be an important step toward this conjecture, but it's not yet the full conjecture. And so to state it, it's well, we have to work a little bit, but I can state you at least two results that are reasonably understandable. So you take the space of smooth functions, space-time, and you endow this space with the following norm. You measure the norm as the norm of f composed by the Schrödinger propagator as an operator from L2 in X to L2 spacetime. So that gives you a norm. Of course, if you take U0 equal 1, then it's very easy to see that your norm is larger than the L2 norm spacetime, simply because the solution to Schrödinger equation associated to 1 is 1. The constant is invariant, and so on the right, you will get the norm of f times 1 L2 spacetime, right? And since you take the sup, your norm is larger than the L2 norm. Now you can also take that the fact that the operator norm is bounded from L2 in X to L2 in L infinity in time with values L2 in X, and that gives you that your norm is smaller than the norm of f L2 in time with values L infinity in X. So you see it's a norm that is in between these two ones. Okay? And now the theorem is that if you take y to be the closure for smooth functions for this y norm, so you have smooth function, you take the closure for this norm, and then as soon as your potential is in y, and as soon as your characteristic function is in y, then you have observation. Okay, so first glance, it looks a very, very abstract result. And the question is, well, can we give some examples? And the answer is yes. So now you have a second theorem, and I will give you examples afterwards. So second theorem is that if you know that you have some uniform integrability for solutions to Schrödinger equations, then y contains all L infinity functions, meaning the conjecture is true. And it's actually equivalent. L infinity is included in y, and then you have observation for any bounded potential and any measurable set, if and only if you have uniform L2 integrability for Schrödinger solutions to Schrödinger equations. Okay. So first, a set of corollaries on the torus. First, the full conjecture is true in dimension 1. You can take any potential in LP as soon as P is larger than 1, and you can take any observation set measurable, and then you observe Schrödinger equation. In dimension 2, you can take any potential which is L2, and then you can take any set of observation which is measurable in time times measurable in X. It's not the same as measurable space-time, but it's still a large class. Okay, and now last corollary, in any dimension, let's say you can take any potential which is continuous, and you can take any observation which is a product of measurable space, measurable sets, but these sets has to be at most two-dimensional, no more. You see, so conjecture is not completely proved, but there is still a project. Okay, so now just a few comments what is the relation with some classical results. So classical result, first there is a big conjecture in dispersive partial differential equations, which is the fact that you have some 3-Hartz estimates without loss for Schrödinger equation on tori for some p. And this conjecture implies our assumption, the uniform L2 integrability. the big conjecture in the set is much stronger actually than our assumption, right? So this assumption is a weak form of the big conjecture by Burq, this one. Second, there is a classical result by Zygmunt, and it was actually the key of the result that I stated at the beginning of the talk, which says that if you take eigenfunctions of the Laplace operator on the torus, T2, then you have uniform L4 norm. L4 norms are uniformly bounded by L2 norms. So it's also kind of an equi-L2 integrability for this. And that gives you, that allows to prove some dispersive estimates with partial things, which are the key to our proof. Okay. So now I have just very rapidly, because I don't want to spend too much time on the proof or on the torus. So maybe I'm going to skip the ideas of the proof on the torus. And then I will go back. That's not the end of the talk. Don't worry. No. I will go back now to trying to explain to you a little bit the proof, not this one. Yes, the proof of this one. The fact that the geometric condition, if you have geometric condition on an open set, then you have observation and hence exact controllability from any time measurable set. Right. So this is the and for this one, what I'm going to do is I'm going to switch to my tablet. So I'm going to stop sharing this one, and then I'm going to share. Yes. Okay, I'm going to share my. Okay. Okay, excellent. Okay, so now what I'm going to do just now is to give you some ideas about the proof of the result when you have exact geometric control. So let me remind you, the geometric control condition, you have your domain, and then you draw the geometric rays. So they travel like that. They reflect on the boundary. And then the assumption is that omega, and then the assumption is that always have to pass through omega after a time t, which is smaller than some fixed t0. Okay? Okay, so under this assumption, you actually have a resolvent estimate, which is like that. So you take minus Laplace minus tau square u equal f implies that norm of u L2 is going to be bounded by c over 1 plus modulus of tau norm of f L2 plus norm of 1 omega u L2. Let's call it D. Okay? So this is the classical resolvent estimate that is known to be true when you have exact controllability. So actually, the classical result, there is many people, so we wrote a version of it with Maciek-Zworski, and it states the following. If you have an observation a resolvent estimate like that, then you have exact controllability that implies observation for any t, observation from 0t times omega for any t finite. Okay, well, so you just have a result like that, and then you deduce observation. Okay, so our result is actually tells you, so to prove this, you actually just need the fact that this function tends to 0 when tau tends to infinity. That's the only assumption you did. As soon as you have this, then you're going to get this result. Okay, and the proof is actually very easy. It's just Fourier. You just perform Fourier in time with some proper time cutoff, and then you get it very easily. Okay? Okay, so our result with Huizhu is that as soon as you have this, it actually implies a stronger version from ET times omega for any ET measurable with positive measure. Right? So it's an abstract result. As soon as you have an observation like that with an assumption like that, meaning that this quantity has to go to 0, then you have observation from any measurable set in time. Okay, so let me explain now to you the scheme of proof. I don't know how many times do I have? Yes, 15 minutes is perfect. Basically, the proof can almost be performed completely within 15 minutes. Okay, so first step is that we revisit the classical proof here. And what we prove is that what it implies is actually better. You have a high frequency estimate observation with observation constant that you control, meaning that you get norm of U0 L2 square is bounded by C integral from 0 to t, and C over t integral on omega of modulus of u tx square dx dt. Okay, so it's now quantifiers. There exist C for any t positive for any u0 with only high frequency. You need to give a proper meaning to the fact that your function has only high frequencies, but it's in the high frequency regime, you have a constant. And you see, this is essentially the best you can hope for, because of course, the integral on omega of modulus of u square dx is bounded by integral on big omega, your domain of modulus of u square, which is the norm of u at time t L2 square, which is the norm of U0, right? And so what you know is that this is always smaller than C over t integral from 0 to t of norm of U0 L2 square, which is C norm of U0 L2 square, right? So the constant here is the best you can hope for. Okay, so the proof is essentially, again, you just revisit the old proof, classical one, and you get this. Step 2. Step 2, what you do is once you have that, it means that for you have to glue high frequency and low frequency, and then what you get is the following. There exists C for any t, or for any t, there exists D depending on t, such that you have an observation with a remainder term is smaller than C over t integral from 0 to t integral on omega of u square dx dt plus dt norm of u0 h minus 10. Oh, h minus 10. Okay, and basically in this term, you put all the low frequency terms. Low frequency, high frequency. Okay, and so the important point here is that your constant here does not depend on t, but this one do depend on t. Okay, and this is just you glue your high frequency part and the low frequency part, and then you're done. Step 3, you take a measurable space in time. Then once you have a measurable space, you know that almost every S0 in ET is a density point. Okay, so what is a density point? It means that the measure of E, your space, ET, intersected with the ball centered at S0 and radius R, divided by the size of the ball, which is 2R, then this goes, when R goes to 0, it goes to 1. Meaning that when you take smaller and smaller balls around S0, then most of the points are in E. You take E, you take the intersection, and then the smaller you take R, the closer you are to the case where you don't have E. Okay, and this is a classical result in measure theory, that almost every point in a set of positive measure is density. You see, it's a surprising result first time you see it, but the proof is not difficult. It's very standard. Okay, so now since most of the points are density, means that there exists an S0 which is density. Okay, and what you do is that you apply this estimate here, except that you are going to apply it not from 0 to t, but you are going to apply it from S0 minus R to S0 plus R, and then t becomes 2R. Okay, everything is time translation invariant, so you can start from S0 minus R. You have an interval now which is of size 2R, so you divide by the size. And of course, this constant is going to depend on R, but you don't care. Okay? So now we switch to step 3. Okay, and what you do is that you insert 1e plus 1e complementary. Okay, and so this is going to be smaller than c over 2r, the integral with 1e, plus the integral with 1e complementary, plus dr the. Okay, so now I'm going to bound this term. And what I just do is that I replace this by omega. So this is going to be smaller than c over 2r. The integral from S0 minus r to S0 plus r of the 1e complementary of norm of u0 L2 square. And so on the right, this is equal to the norm of u0 L2 square times c times, and then I just have the integral in time of this, which is equal to the measure of E complementary intersected with the ball centered at S0 and radius r divided by 2r, right? Okay, and now I go back to my density point. If I take E, I go to 1. If I take E complementary, I go to 0. Right? This is equivalent, essentially, because the full size is 2r, and the sum, so the sum of the two is equal to 2r, and so E complementary over 2r goes to 0. So that means that this quantity goes to 0. Okay, and so now I just write down what I just did. One E, the observation, plus C, norm of U0. Now I have little o of 1 when R goes to 0, plus D, plus dr, norm of U0, L2, age minus 10 square. This is L2. Okay, and now it's essentially finished because I just take R small enough so that this multiplied, so this multiplied by C is going to be smaller than 1/2 the norm of U0 L2 square, right? And so that means that this one, I can put it on the left, and I still get that 1/2 of the norm of U0 L2 square, or norm of U0 L2 square times 1 minus C little o of 1 when R goes to 0 is smaller than, here I have C over 2R, the integral on 1e, integral on omega of U square, plus dr, norm of U0, h minus 10 square, right? And so at the end, this is going to be larger than 1/2. Okay? And so that gives me just an observation, which is I have the observation, and now I have an error term. And now I can finish my, just 1 minute, so I can finish my proof. Step 4, I just have to eliminate this term. Okay? And for that, it's just a uniqueness result. So uniqueness result is the following. So it's a new uniqueness result for solutions to Schrodinger equations. So it's a theorem, which I also do to Huizhu. You take a U solution of Schrodinger equation on a domain, and then you just, if you assume that U on a space-time set is 0 with positive measure, then U is 0. This is always true. Okay, and this uniqueness results allows to eliminate this last term. Just this contradiction argument, you pass to the limit, and then you get the, it's not at this level, so it's not the standard uniqueness compactness result of Bardot, Lebow, and Roche for the people who know these theories. So it's a new result about solutions to Schrödinger equations. Okay, so now just the thing is that just a remark, there is no problem for this proof. You can replace Laplace, could be replaced by Laplace plus first order plus zeroth order plus potential. And everything would work perfectly fine, including this uniqueness result. There's no problem at this level of generality. Okay, so basically what we get is really it's an abstract result saying that as soon as you have a nice resolvent estimate, which is the resolvent estimate you get when you have the geometric control condition, then you can switch from time interval 0t can be replaced by any measurable set in time. Okay, so I think it's a good time to stop, and I thank you very much for your attention.
Thank you, Nicolas, for your very nice talk. It was very interesting. So I don't know if somebody has a question or a comment. I want the paper. That's the first. Can you send me the paper, please?
Actually, so this for this result, the paper is on archive.
Okay, okay.
And the proof is so the nice thing is that the proof is actually 3 pages long.
Okay.
So I think in this description I gave essentially all the ingredients of the proof.
You always explain things very, very well. And then when you try to do that, you say, okay, I don't understand.
No. This one is actually very easy. No, it's really something that it's been. It doesn't. I was very happy with these results precisely for that. It's really a result that we can prove. Of course, we are building on many people's work. So it's of course. So the resolvent estimates are difficult to prove. You see, this estimate here is not easy to prove. This requires a microlocal analysis.
Yeah.
But then once you have the microlocal analysis, well, at least once you have this estimate, you don't have. There's no microlocal analysis whatsoever. Okay. It's really just standard, very classical analysis.
Okay, thank you very much. I don't know if somebody, your name?
No, I only wanted to say that thank you, Nicolas. I have enjoyed your talk. It was interesting, yes. I don't have any specific question, but thank you for your talk.
Thank you.
Okay, if there are not any other question or comment, so thank you very much. I just recall you that on February 11, we have in the same